Somewhere beyond the last flickering stars of the Milky Way, a starship the size of a small city drifts through a darkness so complete that no telescope on Earth could ever find it. Its hull is still intact, its engines still hum, but something is quietly going wrong inside. The air is thinner than it should be. A crop failed 3 centuries ago and never recovered. A repair robot cannot be rebuilt because the machine that built it broke first. The people inside no longer remember Earth. They only remember the ship, and the ship, atom by atom, is forgetting how to keep them alive. This is the true horror of the space between galaxies, not the void outside, the slow, cumulative failure within. If you enjoy stories that stretch your sense of scale and survival to the absolute limit, take a moment to hit that like button and subscribe. It genuinely helps more than you might think, and it keeps journeys like this one possible. Now, settle in and get comfortable. Let's begin. Picture a machine roughly the length of Manhattan, spinning slowly against a background so black that no camera on Earth could ever resolve it. Its outer skin is a lattice of shielding many meters thick, layered with water tanks, regolith, and shredded metal reclaimed from every mission that ever came before. Inside the rotating drum, a strip of engineered land curves upward on either side, disappearing into a false ceiling that hides the axis of rotation. On that strip, 40,000 human beings live out their lives. There are wheat fields, there are freshwater reservoirs, there are schools, hospitals, workshops, cemeteries. There is a sky painted onto the inner shell of the cylinder, and there are stars printed on that sky because the real ones outside have grown too distant to see with the naked eye. This is the reference starship we will follow. Call it a worldship. It moves at approximately 1% of the speed of light, which is a velocity so far beyond current human technology that it may as well be magic. And yet it is the modest end of what serious engineers have ever proposed. It carries fusion fuel in enormous stern tanks, or perhaps antimatter locked inside magnetic bottles, or a solid slug of frozen deuterium the size of a small mountain. The exact answer does not matter yet. What matters is that this ship left its home galaxy long ago, and it is now falling through the empty region between the Milky Way and Andromeda, aiming at a target that will not be reached for approximately 250 million years. 250 million years. Say that number aloud, and it does not shrink. The dinosaurs did not exist that long ago. 250 million years ago, Earth's continents were still assembled into the supercontinent Pangaea, which had not yet begun to tear itself apart. The Atlantic Ocean did not yet exist. Mammals were tiny, rat-like shadows scurrying under the feet of reptiles. Human beings did not evolve until far more recently than the moment this journey would have to begin. And yet, the reference starship we are describing must not merely last that long, it must remain a functioning human world for the entire duration, with breathable air, drinkable water, edible food, viable children, and the industrial capacity to fix itself when things break. If that sounds impossible, hold that feeling. It is going to get worse. Before we can talk about what would kill this ship, we need to talk about where it actually is. And this is the first place where human intuition fails, because between galaxies is not a location. It is a fading. Galaxies do not end at a wall. They do not have a border marked by a line of stars beyond which everything abruptly stops. The Milky Way's bright, familiar disk of spiral arms, the part that shows up in every artist's rendering, is only the visible surface of something much larger. Beyond that disk lies the stellar halo, a diffuse cloud of ancient stars, globular clusters, and streams of debris from galaxies our own has already eaten. Beyond that halo lies another halo, mostly invisible, made of extremely hot gas known as the circumgalactic medium. It stretches for hundreds of thousands of light years in every direction, and beyond even that lies the dark matter halo, which extends farther still, possibly 1 million light years across in total, though it fades so gradually that nobody can point to a single spot where our galaxy definitely ends and something else definitely begins. So when our reference starship leaves the Milky Way, it does not cross a border. It simply passes through zones of decreasing density. The bright stars thin out, then the halo stars thin out, then the circumgalactic gas thins out. Then, somewhere in a region so gradual that even the ship's own instruments would struggle to say when it happened. The vessel finds itself in the true region between galaxies, the cosmic web, the warm, hot intergalactic medium, the vast filamentary structure that connects the galaxies of the local universe like the threads of an enormous three-dimensional spider's web. This region is where our starship spends the overwhelming majority of its journey. This is where survival will be decided. And here is where the illusion begins. The intergalactic medium is, by any reasonable measure, empty. Astronomers estimate that a single cubic meter of it contains on the order of 10 to 100 hydrogen atoms. For comparison, the same volume of air on Earth contains something like 10 to the power of 25 molecules. The intergalactic medium is more diffuse than almost any environment a human being has ever encountered, thousands of times emptier than the best ultra-high vacuum chambers ever built in a laboratory on Earth, and vastly emptier than ordinary air. If you stood inside it, you would feel nothing. You would see nothing. The nearest star from the ship's viewpoint might be tens of thousands of light years away, a smudge behind you where the galaxy you left has become a tiny spiral. Ahead of you, if you are extraordinarily lucky, another smudge the galaxy you are aiming at. Still absurdly far. In every other direction, nothing but darkness broken by other galaxies so distant that their light reaching you is millions of years old. An untrained mind looks at this and thinks, safety. No planets to crash into, no asteroid belts, no solar radiation pressure, no competing spacecraft, no political borders, no pirates, no microbes drifting between star systems, just a smooth, glassy vacuum through which the ship can coast for as long as its engines allow. And this is the assumption we need to break, because it is exactly wrong. The emptiness is not the safety. The emptiness is the danger. The emptiness is the entire problem. To understand why, consider what your civilization actually depends on. Not the visible parts, not the streets and the buildings, the invisible parts. When you turn on a tap in your kitchen, water arrives because a network of pipes, reservoirs, treatment plants, engineers, chemists, technicians and regulators keeps that water flowing. When you eat a piece of bread, that bread exists because millions of hectares of wheat were grown by farmers using fertilizers manufactured in enormous industrial plants, powered by electricity, generated in stations built by welders and machinists, trained in schools, funded by taxes, collected by governments, elected by populations. Every glass of milk, every antibiotic, every semiconductor, every screw and washer and rubber gasket that keeps your world functioning is the visible tip of an industrial and biological pyramid that extends downward through millions of hidden interdependencies, all the way to the raw ores in the ground and the microbes in the soil. On Earth, that pyramid is invisible because it is redundant. If one factory burns down, another factory takes over. If one crop fails, another region ships food. If one engineer forgets a critical technique, another engineer somewhere else remembers. The pyramid is enormous, distributed across an entire planet, and continuously refreshed by roughly 8 billion human beings, each of whom is quietly maintaining some tiny corner of it. Earth's civilization persists because it is huge and because it is connected. Now shrink that pyramid down to fit inside a rotating metal cylinder in the middle of intergalactic space. Take away the 8 billion redundancies, reduce the population to 40,000, remove the entire external biosphere, remove the atmosphere, the oceans, the mines, the forests, the coral reefs, the pollinators, the microbes in the topsoil that keep plants alive. Remove every other country and every other continent. Remove the option to import anything, ever again. The Starship must contain, in miniature, every function that Earth performs, and it must perform them without stopping for a duration measured in geological time. And the moment any single link in that pyramid breaks and cannot be locally repaired, the countdown to the death of the ship begins. That is what the emptiness means. It is not that the vacuum reaches in and kills anyone directly. The vacuum does not need to. The vacuum simply refuses to help. It offers nothing. If a filter clogs, no one is coming with a replacement. If a crop dies, no seed bank on some neighbouring planet can ship you a fresh batch. If the last person who understood how to calibrate the plasma flow through the fusion torch dies without teaching an apprentice, the knowledge is gone. Not misplaced. Not archived somewhere retrievable. Gone. And the ship keeps moving, and the void keeps not caring. This is the correct way to think about intergalactic travel. It is not a distance problem. It is a self-sufficiency problem. Getting to Andromeda is easy compared to remaining human while you are getting there. Now let us look more carefully at our reference ship, because the specific numbers matter. Why 40,000 people? Why not 400 or 4 million? The answer comes from population genetics. Modern research on generation ships, vessels designed to carry multiple generations of humans over centuries or millennia, has converged on a rough consensus that populations below a few hundred people risk catastrophic loss of genetic diversity within a handful of generations. Older studies from the 1960s suggested that as few as 150 carefully managed individuals could preserve enough diversity for a 200-year voyage, but more recent computer modelling by anthropologist Cameron Smith and colleagues has argued that even 10,000 people is a minimum, and that 40,000 is a much safer figure for a genuinely long-duration mission. Below that threshold, random genetic drift causes recessive disorders to accumulate, immune diversity to collapse, and the population to become fragile in the face of disease or catastrophe. 40,000 is also, not coincidentally, roughly the population of a small town. It is enough people to sustain schools, hospitals, workshops, farms, laboratories, and universities. It is enough people to have specialists in different fields: engineers, doctors, biologists, farmers, technicians, teachers, ecologists, without any single person being the sole custodian of any critical skill. And critically, it is few enough people that the ship can plausibly feed, water, house, and maintain them using recycling systems that stay within the bounds of physics. Push the number lower and you lose genetic and cultural robustness. Push it higher and the mass, energy and food requirements begin to explode past what any conceivable propulsion system could carry across intergalactic distances. Why 1% of the speed of light? Again, the answer is compromise. Faster is better in almost every way. Shorter journey, fewer generations, less exposure to cumulative failure, but every increase in velocity demands exponentially more energy. To reach 10% of light speed, our reference ship would need roughly 100 times more kinetic energy than at 1%. To reach half of light speed, thousands of times more. And this energy must be supplied by whatever fuel the ship carries at the start, because there are no refueling stations between galaxies. 1% of light speed is roughly the fastest velocity that most credible engineering studies of world ships have considered plausible using fusion propulsion. Even that is optimistic. Some serious analyses have argued for 0.1% of light speed or lower, which would stretch the journey to 2.5 billion years. For the sake of narrative sanity, we will hold the ship at 1%. And why Andromeda? Because it is the nearest major galaxy to our own, and because it is coming toward us anyway. Andromeda lies approximately 2.5 million light-years away, though its gigantic dark matter halo may already brush against our own. It is on a collision course with the Milky Way in roughly 4 to 5 billion years. The two galaxies will merge into a single enormous elliptical structure that astronomers have already nicknamed. But our ship is not waiting 4 billion years. It is departing now, or in some plausibly near future, and it must cover the distance at its own pace. At 1% of light speed, ignoring cosmic expansion for the sake of simplicity, that means approximately 250 million years of travel. This number will haunt every calculation that follows. Now, let us watch the ship depart. Imagine the moment it clears the last dense region of the Milky Way's stellar disk. The engineers below deck have been running final calibrations for months. The reactors are burning steadily. The rotation section is producing a stable gravitational simulation at 1 Earth gravity along the outer decks. Farms are producing crops. Livestock carefully selected, genetically engineered for low methane output and high nutritional efficiency, are being raised in the animal levels. Children are being born. Elders are dying. The ship has already been in flight for decades by this point, coasting outward through the halo, and the sensation of leaving has been so gradual that most people have not consciously noticed it. But sensors do notice. The density of nearby stars drops. The cosmic ray flux changes character. The ship is no longer sheltered by the galactic magnetic field, which had partially deflected the highest energy particles from more distant sources. The interstellar dust grains that used to occasionally impact the shielding become dramatically less common. Radio noise from stellar sources fades. If you were standing at the forward observation deck assuming the ship had one, which it probably would not, because giving people access to windows is a psychological hazard, you would see the Milky Way behind you as an enormous, tilted disk of light, its center glowing softly, its spiral arms visible as elegant curves of star clusters. Ahead, the void. To the sides, a scattering of other galaxies, each one a smudge of pale light representing hundreds of billions of stars. For the first century of intergalactic travel, life aboard the ship changes very little. The engineers who launched the mission are dead, but their grandchildren are running the ship. Children are being born who have never seen the Milky Way from the inside. A generation grows up, matures, has children of its own, and dies. Then another generation, then another. The ship's clocks tick. The rotation of the drum produces the illusion of gravity. The lights come on and go off according to a 24-hour cycle inherited from a planet that most crew members can no longer point to, because from inside a windowless cylinder, direction has become an abstraction. And here is where the illusion of safety completes itself, because for those first centuries, perhaps even for the first several thousand years, the ship is doing fine. The stored food reserves are still stocked. The stored spare parts are still on the shelves. The recycling systems are running within their design tolerances. The population is stable. The reactors are producing power. Nothing has gone wrong yet, and it is very easy from that vantage point to believe that nothing will. It is very easy to imagine that the ship is a sealed, self-contained bubble of humanity, coasting effortlessly through a vacuum that cannot touch it. The engineers who designed the ship believed this too, because their calculations showed that everything was in balance. But calculations of balance are lies unless they extend across the full duration of the mission. And no honest calculation across 250 million years has ever produced the answer, "We will be fine." The ship is losing things. It is losing them slowly, invisibly, in ways that will not become obvious for centuries. It is losing atoms of water vapor through microscopic leaks in the hull. It is losing tiny amounts of nitrogen as it cycles through the biological systems and gets locked into forms that are hard to recover. It is losing spare parts every time a repair is made and a bolt is stripped or a wire is cut too short and thrown away. It is losing knowledge every time an elderly technician dies before finishing the training of an apprentice. It is losing genetic diversity every time a would-be parent decides not to have children or dies before reproducing. It is losing electronic reliability every time a cosmic ray flips a memory bit, and the error correction algorithm quietly patches over the damage without anyone noticing. Each loss, individually, is trivial. Each loss, across 250 million years, is a countdown. Before we examine what quietly eats the ship in the deep void, we should look more carefully at the region the ship crosses on the way out, because the transition from galaxy to intergalactic space is not a single event. It is a long, gradual descent through progressively thinner environments, each with its own hazards. When our reference starship first pulls away from the stellar disk, it enters the halo, a diffuse spherical region containing ancient stars, globular clusters, and streams of debris from smaller galaxies that our Milky Way has already consumed. The star density here is thousands of times lower than in the disk, but not zero. The ship will pass, occasionally, within a few light years of individual halo stars. Each such encounter is a minor navigational event and a minor radiation event, because halo stars are old, generally quiet, and rarely produce dangerous flares. These are the last real stars the ship will see up close. Beyond the stellar halo lies the circumgalactic medium, a vast reservoir of hot gas that surrounds our galaxy in a pillowy envelope extending hundreds of thousands of light years outward. This gas is thin, thinner than the interstellar medium inside the disk, but not as thin as the true intergalactic void. Its temperature is somewhere between 100,000 and 1,000,000 Kelvin. Its composition includes hydrogen, helium, and small quantities of heavier elements ejected by ancient stellar explosions. The ship experiences the circumgalactic medium as a mild but measurable drag on the forward buffer and as a source of slow, steady ionization damage to any exposed surface. This phase of the journey lasts thousands of years. The ship has not yet reached the true intergalactic emptiness, and it has already left everything that could conceivably be called home. From here onward, the density of matter outside the hull only decreases. The ship is descending, not into a wall, but into a gradient, and the far end of that gradient is where the true crossing begins. Consider the modest baseline of what humanity has already demonstrated in space. The International Space Station has run a partially closed life support system for over 2 decades. Its environmental control and life support system, known by the acronym ECLSS, was originally designed to recover about 85% of the water that the crew consumes. Through years of refinement, including the addition of a brine processor that squeezes water out of the residue left behind by urine processing, NASA announced that the system had reached approximately 98% water recovery. That number is celebrated, and it should be. It represents a monumental achievement in closed-loop engineering. It also represents a floor, not a ceiling, of what human life support technology has actually accomplished at scale. Every single day, the station still consumes small quantities of water, oxygen, and other consumables that must be shipped up from Earth on cargo missions. If those cargo missions stopped, the station would not last very long months at best, depending on stored reserves. Our reference Starship must do vastly better than the station. Not marginally better, vastly better. It must recover not 98%, but effectively 100% of every consumable it uses, every day, for 250 million years. And when we say effectively 100%, we mean it. Because if the ship recovers only 99.9% of its water on each cycle, and the cycle takes a day, then across even a modest span of 10,000 years, the losses compound into a shortfall of a large fraction of the ship's total water. Across 250 million years, 99.9% recycling would leave the ship with essentially no water at all. The math is merciless. Recycling that would be considered miraculous by every current engineer on Earth is still not remotely good enough. This is what the Void does. It does not attack. It waits. It allows the ship to fool itself for centuries, watching the small losses accumulate, until one day, perhaps thousands of years into the voyage, perhaps millions, a critical threshold is crossed, and something that had been quietly draining suddenly runs out. And then the ship discovers with horror that it can no longer produce what it needs to survive, and that the nearest source of resupply is a distance so far that no rescue mission could ever arrive in time. Now imagine yourself as the captain of the ship, an entirely honorary role, because by the time the vessel is deep in intergalactic space, no single human is really in charge of anything. The ship is run by committees, algorithms, and traditions passed down for generations. But imagine yourself standing on the observation platform of the axis of rotation, looking out along the length of the cylinder. You can see the strip of farmland curving up above your head, the small towns clustered along it, the artificial rivers, the parks. You can see the reactor bay at the aft end, a locked and shielded section that most crew members never enter. You can see the maintenance workshops, the medical facilities, the schools, the libraries. You can see everything the ship contains. And then imagine trying to explain to yourself what is not there. There is no ocean. Not really. There is a large reservoir, but it does not have currents driven by planetary rotation and lunar tides. There is no atmosphere. Not really. There is a pressurized volume of air, but it does not have the enormous thermal buffering capacity of a real sky. There is no soil. Not really. There is engineered growth medium, refreshed by carefully managed microbial cultures, but it does not have the deep, complex, multi-billion-year evolutionary history of a real ecosystem's dirt. There is no wilderness. There is no place a person can go where they will not eventually be found. There is no source of anything except the ship's own inventory. Everything the ship contains, it must keep or make from what it has already kept. And the ship is now, at this moment in our story, still very early in its journey. It has crossed the halo. It has entered the region of the cosmic web. It has begun the true intergalactic phase of the mission. Sensors are reporting normal operation. The population is thriving. The reactors are humming. The ship is holding together. But somewhere in the hydroponic bays, A strain of algae is beginning to evolve away from its original genetic profile, and no one has noticed yet. Somewhere in the water reclamation system, a valve that was manufactured on Earth 2,000 years earlier is starting to experience microscopic wear that will not fail for another 800 years, but that has already begun. Somewhere in the fusion fuel reserves, the outermost tank of frozen deuterium is a fraction of a percent below its design temperature because of a slow thermal drift that no one caught during the last inspection. Somewhere in the ship's memory banks, a cosmic ray has just flipped a bit in a copy of the ship's technical archive, and the error correction software has silently corrected it. But the same cosmic ray has also caused a slightly different bit in a redundant backup, and the reconciliation algorithm has picked the wrong version. None of these tiny anomalies will kill anyone today. None of them will kill anyone this century. But they are the first whispers of what is coming, and they are the reason the void between galaxies is not safe. Because out here, in the vast filamentary emptiness of the cosmic web, the ship cannot rely on the outside universe for anything. It must generate every solution from what it already carries. And what it already carries is finite. The reactors keep burning. The rotation keeps producing gravity. The farms keep growing crops. The children keep being born. The Milky Way behind the ship shrinks by the tiniest fraction each year, and Andromeda ahead of the ship grows by the tiniest fraction each year. The journey has barely begun. The first century of true intergalactic travel is passing without incident, and somewhere deep in the hull, in a place no one is currently looking, the first thread in the pyramid of civilization has begun quietly to fray. 3,000 years into the journey, an engineer named on ship's records simply as Lyra, because family names have long since compressed into single syllables, the way surnames sometimes do across long isolated communities, walks into the forward sensor, bay, to investigate an anomaly. She is the 5th generation of her family to hold the position of external systems monitor. Her great-great-grandmother held the same title when the ship crossed what the archives call the halo boundary, though nobody alive has ever seen a halo or knows exactly what the word originally referred to. Lyra runs a diagnostic on the forward shielding. The reading comes back with intolerance. She notes it in the log and moves on to the next task. She has no way of knowing that the number she just recorded is not the same number her great-great-grandmother would have recorded. The forward shielding is 1 micrometer thinner than it was when the ship departed. Across 3,000 years, 1 micrometer is nothing. Across 250 million years, at the same rate of erosion, it becomes a wall that no longer exists. To understand what is quietly eating the front of the ship, we have to look at what empty actually means in the region between galaxies. Because the emptiness is a lie of language. The vacuum outside the hull is not truly a vacuum. It is a thin, ionized soup that has structure, temperature, motion, and critically a small but stubborn population of particles that the ship is running into at 3,000 kilometers per second. Astronomers refer to the diffuse gas that fills the space between galaxies as the intergalactic medium. Within the filaments of the cosmic web, this gas takes a specific form that has become one of the most studied phenomena in modern cosmology. The warm, hot intergalactic medium, known by researchers as the WIM. Peer-reviewed observations and cosmological simulations agree that the WIM has a temperature between roughly 100,000 and 10 million degrees Kelvin. 10 million degrees. On paper, this sounds like flying a ship through a furnace. In practice, the ship's crew never feels it, and the reason is a fact about temperature that most people never learn in school. Temperature, in physics, is not the same as heat. Temperature is a measure of how fast individual particles are moving. Heat is the total energy those particles can transfer to something else. A single spark from a welder can be at several thousand degrees, but it will not burn down your house because there is not enough mass in the spark to transfer meaningful energy. The intergalactic medium is exactly like this, taken to a cosmic extreme. Its particles are moving fast enough to qualify as 10 million degree plasma, but there are only about 10 to 100 hydrogen ions in every cubic meter. If you swept a volume of intergalactic gas the size of the Earth into a jar, you would collect enough matter to make a small marble. The temperature is real, the heat delivery is negligible, so the crew inside the rotating drum does not roast. There is no shockwave, no bow flame, no dramatic external friction. In fact, from any distance, The ship looks perfectly cold, radiating waste heat outward through enormous panels at the temperature of a lukewarm bath. Space between galaxies is not a fire. It is a very slow, very quiet form of erosion. But erosion is still erosion. Every hydrogen ion the ship encounters at 3,000 kilometers per second delivers a small but non-zero amount of kinetic energy to the forward shielding. Every helium ion delivers more. Every stray oxygen ion seeded into the WIM over billions of years by ancient stellar generations delivers more still. Across a century of travel, these impacts are trivial. Across a million years of continuous impact at cruise velocity, they add up to a slow sandblasting of the forward hull. The ship must budget for this. Every worldship design ever seriously proposed has included a forward buffer, sometimes a block of ice, sometimes a plate of steel, sometimes a magnetic field, sometimes a cloud of ejected dust generated by the ship itself as a sacrificial shield. Whatever the architecture, it exists to be eaten, and once it is eaten, it must be replaced. That is where the trouble starts. Because replacing a forward buffer requires either carrying spares for the full duration of the journey or manufacturing new buffer material from raw stock carried on board. 250 million years of continuous erosion means the ship must either carry a truly enormous inventory of shield mass or possess the industrial capacity to keep making more. Neither option is simple, neither option is small, and erosion by ionized gas is only one of the external threats. The others are worse. Somewhere between our home galaxy and Andromeda, drifting through the cosmic web, are microscopic grains of dust. They were forged in the outer layers of ancient stars that died billions of years ago, blasted into the intergalactic void by supernovae, and have been coasting through emptiness ever since. Their density in intergalactic space is very low, much lower than within galaxies, but they are not absent. Confirmed observations from spacecraft like Ulysses and Cassini detected interstellar dust grains streaming through our own solar system at approximately 26 kilometers per second grains that originated inside our own galaxy. The intergalactic population is thinner and less well characterized, but it exists, seeded by ancient stellar explosions across billions of years. And the reference Starship is not moving at 26 kilometers per second. It is moving at roughly 3,000 kilometers per second. Kinetic energy scales with the square of velocity. A dust grain that would deliver a mild sting at interstellar speed delivers a very serious impact at intergalactic cruise. A grain the mass of a single grain of table sand, striking the forward shielding at 1% of light speed, releases energy comparable to a small chemical explosive. A grain the size of a pea would punch through anything not specifically designed to absorb it. Even a grain the mass of a single bacterium delivers roughly the impact of a rifle bullet. These are not events the ship can afford to experience often. Fortunately, the intergalactic dust density is low enough that such impacts are rare, perhaps a handful across a lifetime, perhaps hundreds across the full journey, depending on the local density of whatever cosmic filament the ship is currently traversing. But rare is not the same as never. And here is the deeper problem. Because the ship is moving so fast, it cannot see incoming grains in time to react. A dust particle drifting in the ship's path is invisible until it hits, because the light reflected off it is arriving only fractionally faster than the grain itself. No early warning system will ever be fast enough. The ship cannot dodge, it can only absorb, and every impact leaves a crater, however small, in the forward armor. This is the first hidden cost of intergalactic velocity. The faster you go, the emptier space needs to be, and the emptier space is not empty enough. Some worldship studies have proposed slowing down for this reason, dropping to 1,000th of light speed, accepting a journey of several billion years in exchange for reduced impact damage. Some have proposed magnetic shields that deflect ionized particles, though these are ineffective against neutral dust. Some have proposed a leading probe that flies ahead of the ship, sweeping a corridor clean, though this multiplies the fuel budget. There is no clean solution, there is only budgeted damage. Now let us turn our attention inward, to the electronics that run every subsystem on the ship, because the second thing quietly eating the vessel is not something outside it at all. It is the background radiation environment itself. Within the disk of our galaxy, The Sun's heliosphere partially shields the solar system from the highest energy cosmic rays. The Sun's magnetic field, blown outward by the solar wind, forms a protective bubble that deflects a significant fraction of the incoming particles. Even so, the highest energy cosmic rays punch straight through this bubble as if it were not there. In intergalactic space, there is no heliosphere. There is no protective bubble. The ship is exposed permanently to the raw galactic and extragalactic cosmic ray flux without any solar filtering whatsoever. The energetic particles are relentless. They pass through the shielding, through the crew quarters, through the hydroponic bays, through the electronics, through the human bodies inside everywhere, always, at every moment of the voyage. Human bodies, in the short term, can handle a modest cosmic ray dose. In the long term, the accumulated damage causes cancers, cellular mutations, and gradual degradation of tissues. The ship must protect its crew with meters of shielding likely water tanks, doubling as radiation absorbers and as reserves for the life support system. This is a solved problem in the sense that we know how to do it, though executing it on the mass scale required for a world ship remains untested. But the electronics have no such easy fix. Modern computer chips are built with transistors so small that a single high-energy particle passing through a chip can flip a bit, corrupt a calculation, or in rare cases physically damage a transistor beyond repair. In the aerospace industry, this is a well-known problem. Every spacecraft ever launched has to deal with it. Voyager 1 and Voyager 2, humanity's most enduring deep space missions, have been running for nearly 50 years now, and their engineers have documented in detail how the electronics have degraded over that time. Recent published analyses of Voyager telemetry show that the radioisotope thermoelectric generators, the plutonium-powered heat sources that generate electricity aboard the spacecraft, have lost roughly 40% of their original output. Radio frequency transmitter power is down roughly 15%. Sensor calibration has drifted by measurable amounts. And in November of 2023, Voyager 1 suddenly began transmitting gibberish, forcing engineers at the Jet Propulsion Laboratory to conduct a months-long detective operation that eventually traced the problem to a single failed memory chip in the aging flight data subsystem. The mission survived only because human engineers on Earth were able to remap the ship's software around the dead component, transmitting new instructions across billions of kilometers of space. Voyager is a probe. It is not a habitat. It is not a civilization. It carries no biological ecosystem, no manufacturing capability, no children. It is a tin can with a radio and a plutonium battery, and after less than 50 years of operation, its own designers acknowledge that it is running on borrowed time. Consider what this means for a Starship expected to operate not for 50 years but for 250 million years. The Voyager mission has already outlived its original design lifetime by a factor of 10. The worldship must outlive its design lifetime by a factor closer to 1,000,000. Every failure mode Voyager has taught us about memory chip degradation, transmitter power drop, thruster wear. Sensor drift has to be either engineered out of the ship entirely or made repairable indefinitely from onboard resources. That word indefinitely is where the physics of long-term repair collides with the reality of an isolated industrial system. A ship that carries spares can last as long as the spares hold out. A ship that can manufacture spares from stored raw material can last longer, so long as the manufacturing equipment itself does not fail. A ship whose manufacturing equipment can build replacement manufacturing equipment can last longer still. But at some point, if the mission is long enough, even the deepest layer of self-repair fails, because the tools that build the parts are all subject to the same background degradation as everything else. There is no escape from entropy in a closed system. There is only the postponement of entropy through the export of disorder, and in intergalactic space there is nowhere convenient to export the disorder to. This is why the emptiness matters so much. Inside a galaxy, a damaged ship can theoretically limp to a nearby star system and mine an asteroid for raw material. In intergalactic space, there is no asteroid. There is no nearby anything. There is only whatever the ship is already carrying. And whatever the ship is already carrying is finite. Let us turn now to the power system, because this is where the physics becomes most cruelly restrictive. Every proposed method of powering a starship across intergalactic distances runs into the same fundamental barrier. No external energy source is available, and the internal energy source must last essentially forever. Solar power is out, there is no sun. Even during the halo crossing, the parent galaxy is receding fast enough that its combined light is millions of times fainter than sunlight at Earth. By the time the ship enters the true intergalactic void, the light from the entire Milky Way, from any distance the ship has reached, is dimmer than starlight at the edge of our solar system. Solar panels would produce negligible power. They are useless. The ship must generate its own energy from stored fuel. Nuclear fission is a possibility, but only for a limited duration. Uranium and thorium reserves on board would be finite, even with breeder reactor architectures that convert fertile isotopes into fissile ones. The practical operational lifetime of a fission-powered worldship is on the order of thousands to perhaps millions of years, depending on how much fuel was loaded and how efficient the reactor is. 250 million years is beyond reach, and uranium mines do not exist between galaxies. Nuclear fusion is more promising, because deuterium, a hydrogen isotope that fusion reactors can burn, is far more abundant than uranium and can be stored in truly enormous quantities. A worldship-scale fusion reactor operating steadily could plausibly power the vessel for millions of years, perhaps tens of millions, before running out of fuel, but it will not power the ship for 250 million years without refueling, and there is nowhere to refuel. Some designs have proposed collecting stray hydrogen from the intergalactic medium using a scoop, a variant of the classic Bussard ramjet concept from mid-20th century speculative engineering, but the density of the intergalactic medium is so low that the scoop would need to be absurdly large and would produce more drag than it produced useful fuel. Recent analyses have generally concluded that Bussard-style ramjets do not work in interstellar space, let alone intergalactic space. Let us put actual numbers on the dust impact problem, because the physics is unforgiving in a way that abstract description does not capture. A dust grain massing 1 milligram, the mass of a large snowflake striking the ship at 1% of light speed, carries a kinetic energy of roughly 4.5 megajoules. That is comparable to the energy of a small car crashing at highway speed, delivered into a single point in an instant. A grain massing 1 gram, about the mass of a paperclip, delivers roughly 4.5 gigajoules, comparable to the detonation of 1 ton of high explosive. A grain the mass of a marble, at cruise velocity, delivers energy comparable to several tons of high explosive. The intergalactic dust density is low enough that marble-sized impacts are essentially never expected across the full mission. Milligram-scale impacts, however, may occur many times. Sub-milligram impacts grains, massing micrograms or less, occur far more often, perhaps continuously as a fine sandblasting effect. The ship's forward defense must handle all of these scales simultaneously. Against fine sandblasting, a thick sacrificial buffer works well, a slab of ice or a matrix of low-cost material that can be periodically renewed. Against milligram impacts, the buffer must be thick enough to fully absorb the impact energy without allowing debris to spill through to the pressurized hull behind. This is the same principle as a Whipple shield, invented in the 1940s for spacecraft protection, in which an outer layer vaporizes the incoming particle and a second, spaced layer absorbs the expanding cloud of debris. Against rare larger impacts, no passive shield is adequate. The ship must either detect the incoming grain in time to deflect it, probably impossible at cruise velocity, or accept a small statistical probability of catastrophic penetration across the full mission duration. Every worldship study that has looked at this problem has concluded that some fraction of missions must be expected to fail through unlucky impact events. The reference ship, at 40,000 tons of forward shielding, might reduce this probability to a few percent across the full crossing. It cannot reduce it to zero. Antimatter is the most energy-dense option physicists know of. A kilogram of antimatter reacting with a kilogram of ordinary matter releases roughly the same energy as several megatons of chemical explosive. A small quantity of antimatter could, in principle, power a worldship for very long durations. But antimatter is extraordinarily difficult to manufacture. Humanity has produced less than a gram of it in total, across decades of particle physics research, and even more difficult to store, because it annihilates on contact with any ordinary matter. A worldship would need to carry its antimatter in perfectly stable magnetic bottles that could not fail even once across the full duration of the journey. A single leak would destroy the ship instantly. There is a related problem that most people never think about, which is that every gram of fuel the ship burns produces waste heat that must be radiated away, and radiating heat in intergalactic space is not as simple as it sounds. The ship's reactor produces electricity, but no reactor is perfectly efficient. A substantial fraction of the fuel's energy emerges as heat rather than useful power. That heat must go somewhere. Inside the ship, it warms the crew, drives the life support processes, and cycles through the various biological subsystems. But eventually, all of it must leave the ship, because if it did not, the interior temperature would rise without bound until the crew died and the electronics melted. The only way to shed heat in a vacuum is through infrared radiation. The ship must therefore have enormous radiator panels extending from its hull, glowing dimly in the infrared at temperatures somewhere between 0 and 100 degrees Celsius. These panels have to be extremely thin, because thick radiators are inefficient. They have to have enormous surface area, because the amount of heat radiated scales with area, and they have to be pointed away from any external heat source, because they can only radiate net heat if their surroundings are colder than they are. In intergalactic space, the surroundings are the cosmic microwave background at approximately 2.7 Kelvin. This is close to the coldest possible reference temperature in the universe, which is actually helpful for the ship's radiators. They can dump heat efficiently, but the radiator panels themselves are permanently exposed to the same dust impacts and cosmic ray flux as the rest of the hull, and cannot be armoured. Every radiator panel is a delicate, essential, wearing organ of the ship, and every radiator failure is an existential problem the crew must fix before the interior overheats. So the power problem, honestly stated, is this. Fusion probably gets the ship most of the way. Antimatter might get it further if humanity ever figures out how to make and store the stuff at scale, and nothing yet proposed gets it comfortably across the full crossing to Andromeda. The reactor will keep humming for a very long time, but somewhere along the journey, perhaps well before the destination is reached, the reactor will run low, and the ship will face a choice between slowing down its energy consumption, shutting off non-essential systems, and eventually perhaps coasting the rest of the way in a semi-dormant state with only the most critical systems still running. Which brings us to thermal control, one of the least glamorous but most essential problems on any long-duration spacecraft. Every process on the ship, human bodies breathing, reactors burning fuel, lights glowing, computers computing, farms growing crops, water being recycled, generates waste heat. In an atmosphere, heat can be removed by convection or conduction. In space, the only way to remove heat is by radiating it away as infrared light. The ship must have enormous radiator panels extending from its hull, glowing dimly in the infrared, dumping waste heat into the void. These panels are among the most vulnerable parts of the ship, because they must have enormous surface area exposed to the outside, which means they are exposed to dust impacts, radiation damage, and micrometeoroid erosion. And they cannot be armoured, because armour would prevent them from radiating heat. They must remain thin and exposed, and they must last. If the radiators degrade, the ship's internal temperature rises. If the internal temperature rises, the crops fail. If the crops fail, the crew starves. The relationship between an exposed sheet of metal in the intergalactic void and a family sitting down to a meal in the ship's residential district is not obvious to the family, but it is absolute. Every meal aboard the worldship exists because the radiators are still working. Navigation is another quiet problem. Within a galaxy, a spacecraft can navigate by observing stars. Their positions are known, and their apparent motion can be used to determine the ship's velocity and heading. In intergalactic space, this becomes vastly harder. The nearest stars are the ancient stars of the Milky Way's outer halo, dimming behind the ship. Ahead, Andromeda is still a smudge. In every other direction, distant galaxies serve as reference points, but they are so far away that even large motions of the ship produce almost no parallax against them. The ship must navigate by pulsars, the rapidly spinning neutron stars, whose radio pulses provide precise timing signals detectable across enormous distances, or by inertial reference systems calibrated at launch and maintained across the full duration of the journey. Both methods work in principle. Both accumulate errors across geological time. A small navigation error, uncorrected, could send the ship missing Andromeda by hundreds or thousands of light years, adding millions of years to the arrival time. And there is another cost the ship pays every day, one that most people never think about. Communication with home is essentially impossible. Even at the speed of light, a message from the Milky Way to a ship halfway to Andromeda takes over 1,000,000 years to arrive. By the time the message arrives, the civilization that sent it may no longer exist. By the time a reply is sent, the recipients may not remember why the message was originally sent. The ship is alone. Not just physically alone, but temporally alone, cut off from any meaningful exchange with any other human civilization that might still exist somewhere behind it. If the Milky Way's civilization collapses during the journey, the ship will not know for millions of years. If a new civilization rises, the ship will not know for millions of years. The crew lives in a perpetual present, an eternal now, disconnected from every history and every future outside the hull. Lyra, in the sensor bay, is completely unaware of any of this in the moment. She sees a normal reading. She logs it. She goes home to her family's small apartment in the residential ring. Above her, on the curved landscape of the rotating drum, other people are living their lives, growing food, teaching children, repairing machinery, writing books that no one outside the ship will ever read. The ship is functioning. The lights are on. The gravity feels right. The air smells fine. For a moment, if you did not know what was outside the hull, you could almost believe you were in a small city on Earth. But the ship is holding together only because its inheritance is still large. The reserves of fuel, spare parts, seeds, chemicals, and stored knowledge that were loaded at launch are still substantial. The engineers have been careful. The recycling loops are 99-point-something% efficient. The crew is disciplined. The systems have been well maintained. And yet the ship is losing atoms every day. It is losing them to microscopic hull leaks, to reaction products locked into unrecoverable chemical forms, to radiation-induced degradation of biological samples, to slow evaporation of stored lubricants, to accidental discards during maintenance, to the outward flowing exhaust of the propulsion system. The mass of the ship is very slowly decreasing. The composition of what remains is very slowly shifting. The library of stored raw materials, prepared with such care before departure, is very slowly losing entries. Nothing has broken yet, but things have begun to wear. The forward buffer is thinner, the radiators are slightly less efficient, the main computers are running a version of their operating system that has been silently patched thousands of times to work around damaged memory sectors. The fusion fuel reserves are lower by a measurable percentage. The ship's inventory of certain rare elements used only in tiny quantities but essential to specific electronic components has been dipped into and cannot be fully replenished. The crew members responsible for tracking these details have handed off their duties to successors who inherit spreadsheets and traditions rather than direct memory of what the original values were. Some numbers, once carefully monitored, are no longer monitored because whoever cared about them has been dead for 800 years. The Milky Way behind the ship has become a smaller, dimmer disk. Andromeda ahead has become a slightly larger, slightly brighter smudge. The ship has crossed perhaps 1% of the total distance. 247 million years of travel remain. The external environment is holding. The hull is holding. The systems are holding. But somewhere inside, in a place no external instrument can measure, the true clock has been running the whole time. And that clock has almost nothing to do with what is happening outside the ship. It has everything to do with what is happening inside. Inside the biology, inside the ecosystems, inside the human beings themselves, inside the fragile web of maintenance and manufacturing and knowledge that has to keep reproducing itself for longer than any civilization on Earth has ever remained continuous. That is the clock that will decide the mission, and that clock is where we go next. 28,000 years into the journey, a farmer named Vess kneels in a hydroponic bay on Ring 7 and stares at a tomato that will not ripen. The vine looks healthy. The nutrient solution tests with intolerance. The lighting spectrum matches what the archives call the reference profile. And yet, 3 seasons in a row, this particular cultivar has produced fruit that stays green for months, then rots on the stem without ever turning red. The strain has been in continuous cultivation aboard the ship for over 20,000 years. Something in it has quietly changed, and no one can say what. Vess makes a note in the agricultural log. The note joins 10,000 other notes, filed across the last several centuries, describing small ecological anomalies that individually mean nothing and collectively mean everything. A pollinator species that no longer visits a particular flower, a soil microbe that has vanished from the samples without explanation, a grain variety that now requires twice the phosphorus it used to require and produces half the yield. None of these problems are catastrophic. All of them are drift, and drift aboard a closed ecosystem sealed off from every possible corrective input is a one-way process. Things do not undrift. To understand why the interior of the ship is where the mission is most likely to die, we have to abandon the intuition that closed ecosystems are simple. On Earth, when we think of the biosphere, we usually think of forests and oceans and grasslands, big obvious systems full of visible plants and animals. But the biosphere is not just those visible things. It is a vast, dense, unbelievably complex web of microscopic and molecular interactions that has been evolving continuously for approximately 4 billion years. Every square centimetre of healthy topsoil on Earth contains, by rough estimate, billions of individual microorganisms belonging to tens of thousands of distinct species. Every drop of ocean water contains millions of viruses. Every breath you take passes through a chemical environment that was shaped by cyanobacteria 2.5 billion years ago and is being continuously refreshed by trees, algae, plankton, and countless other organisms working in coordination across an entire planet. That system is what our reference Starship is trying to replace, with a set of hydroponic bays, algae tanks, soil beds, animal enclosures, and a carefully curated collection of seed stocks and microbial cultures brought from Earth. The scale mismatch is staggering. Earth's biosphere is roughly 1 trillion times more massive than anything that could plausibly fit inside a rotating cylinder in intergalactic space. The ship's ecosystem is not a smaller version of the biosphere. It is a fundamentally different kind of system, thinner, less redundant, missing enormous categories of organisms that a real biosphere would contain. And it has to keep functioning for 250 million years. Consider what humanity has actually achieved in closed ecosystem experiments. The most famous attempt, Biosphere Two in Arizona, sealed 8 people inside a large glass structure in 1991, with the goal of surviving for 2 years using only recycled air, water, and food. The experiment failed on almost every measure. Oxygen levels crashed and had to be replenished from outside. Carbon dioxide fluctuated wildly. 19 of the 25 vertebrate species inside went extinct. Most pollinators died. Cockroaches and ants multiplied catastrophically. The crew members lost significant weight. Personal conflicts fractured the group. And this was on Earth, in a sealed facility that could be inspected from outside, with a rescue option available at any time, and a duration of only 2 years. The reference Starship must do infinitely better, for infinitely longer, with no rescue option at all. More recently, projects like the European Space Agency's Melissa program, a decades-long research effort into closed-loop life support based on interconnected biological compartments, have made progress on individual pieces of the puzzle. Algae reactors can convert carbon dioxide to oxygen with impressive efficiency. Microbial systems can process urine and solid waste into usable nutrients. Higher plants can be grown in enclosed environments with tightly controlled inputs, but no one has ever demonstrated a fully closed loop that runs for years, let alone millennia, let alone geological time. The best long-duration closed system humanity has ever operated is the International Space Station, and as noted earlier, even that requires constant cargo resupply from Earth to keep functioning. So the ship's ecosystem is, at the moment of departure, already an experiment operating well beyond the boundary of anything ever tested. The engineers who designed it have made every conservative choice they could think of. They have loaded seed banks with thousands of plant varieties in the hope that if one strain fails, another can replace it. They have loaded microbial cultures representing hundreds of thousands of species, cryogenically preserved, ready to be revived if the active populations collapse. They have built the hydroponic bays with modular design so that a diseased section can be sterilized and restarted from stored samples. They have created redundant water and air processing loops so that a single failure cannot cascade. Every conservative choice has been made. And yet, the ecosystem is still finite, still closed, still subject to the merciless mathematics of long-duration drift. The most vulnerable element in the ship's biology is not any single species. It is the invisible cycling of chemical elements through the various loops that keep everything alive. Nitrogen has to move from atmosphere to plants, to animals, to waste, to soil, to atmosphere. Phosphorus has to move from stored rock to plants, to bodies, to waste, to recovered fertilizer, to plants again. Carbon has to move between the atmosphere and the biosphere at a rate that keeps oxygen and carbon dioxide in balance. Sulfur, potassium, calcium, magnesium, iron, and dozens of trace elements all have their own cycles. On Earth, these cycles are driven by planet-wide geological processes, volcanoes releasing gases, oceans absorbing carbon, weathering of rocks exposing nutrients, tectonics recycling ancient sediments. On the ship, all of these processes must be replaced by human-designed machinery and biological subsystems, and every gram of every element must be recovered from every waste stream, indefinitely, or the cycles begin to unbalance. Phosphorus is the element engineers worry about most. It is essential to every living cell, and it does not exist as a gas at normal temperatures. It cannot be extracted from the atmosphere the way nitrogen can. It has to be tracked as a solid or dissolved compound through every biological process on the ship. If phosphorus gets locked into a form that the recovery systems cannot break down, bound into calcium deposits in bone, sequestered in dried sludge in a filter, precipitated as an insoluble salt in a pipe that no one thought to inspect, it is lost. The reserves in the ship's stockroom are finite. Every year, some small amount of phosphorus fails to complete its cycle. Every year, the total pool available for use shrinks by an unmeasurably tiny fraction. Across 10,000 years, still unmeasurably tiny. Across 10 million years, the shortfall begins to matter. Across 250 million years, it becomes a slow strangulation of every living thing aboard. Nitrogen has its own version of this problem, and the nitrogen cycle is less forgiving than most people realize. On Earth, atmospheric nitrogen is enormously abundant. Nearly 78% of the air is nitrogen gas, but nitrogen gas is chemically unreactive, and living things cannot use it directly. Instead, specialized bacteria fix atmospheric nitrogen into ammonia, which plants then convert into proteins, which animals then eat, digest, and eventually return to the soil as waste, where other bacteria complete the cycle by converting the compounds back into atmospheric nitrogen. Aboard the ship, this cycle has to be reproduced by a combination of bacterial cultures in the soil and hydroponic beds, along with backup chemical processes that can fix atmospheric nitrogen mechanically if the biological pathway fails. If any part of this system drifts, if the nitrogen-fixing bacteria evolve away from their original function, or if the atmospheric composition slowly shifts, or if some intermediate compound accumulates in an unrecoverable form, the crops begin to fail. Not dramatically, just less well, fewer proteins in the wheat, lower yields per hectare, slightly weaker children. The carbon cycle is more forgiving in some ways and less in others. Carbon dioxide from human breathing must be scrubbed from the air and returned to the plants, which convert it back into oxygen through photosynthesis. This loop is relatively easy to maintain in the short term, but carbon does not only cycle through the atmosphere, it also gets locked into structural materials, into stored crops, into the bodies of the crew, into waste products that resist decomposition. Every century, some measurable quantity of carbon becomes inaccessible to the active biological loop and must be replaced from the ship's reserves. Pharmaceutical manufacturing adds another layer of quiet complexity. The crew will need antibiotics, painkillers, anesthetics, cancer treatments, insulin, thyroid hormones, contraceptives, and dozens of other medically essential compounds. Each of these has to be either manufactured from stored precursors or synthesized biologically from cultivated organisms. The chemistry involved is not trivial. Any medical compound the ship loses the ability to produce is a category of illness the crew can no longer treat. The same logic applies to essentially every other element the ship depends on. Nitrogen can be lost as inert atmospheric compounds that the recovery systems cannot efficiently process. Sulfur can be lost in outgassing from the wastewater plants. Trace metals can be lost in wear particles from machinery, scattered across the ship in quantities too small to recover. Each individual loss is trivial. The sum of all losses, integrated across millions of years, is fatal. Now consider the biological populations themselves. The ship carries humans, of course, but also crops, livestock, pollinators, soil organisms, and probably a considerable menagerie of species chosen for their ecological utility. Every one of these populations is subject to the same problem. They are finite, isolated, and evolving. Evolution does not stop just because a species has been placed on a spaceship. It accelerates in some ways and slows in others, but it does not stop. The wheat growing in Ring 4 is not the same wheat that was loaded at departure. 28,000 years is enough time for hundreds of generations of wheat, each generation subject to selection pressures unique to the shipboard environment. The wheat has been selected, unconsciously, to thrive in the ship's specific lighting spectrum, humidity, gravity, and pest ecology. It has been selected to fail in ways the ship's farmers do not detect, and to succeed in ways they reward. It has drifted. It is still wheat. But it is not the wheat that was loaded, and if the original seed stock in cryogenic storage were revived tomorrow, the two varieties would not necessarily be compatible. The same is true of every other species. The pollinators have drifted, the soil microbes have drifted, the livestock has drifted, the gut bacteria inside every human aboard the ship have drifted, and the humans themselves, this is the most uncomfortable point, have drifted as well. Population genetics tells us what happens when a small, closed population reproduces in isolation across many generations. Random genetic drift causes some traits to become more common and others to disappear, not because those traits are advantageous, but simply because a small population is subject to statistical fluctuations that a large population is not. Modern computer modelling by anthropologist Cameron Smith and colleagues, published in peer-reviewed studies on multi-generational voyaging, has concluded that starting populations below roughly 10,000 people lose substantial genetic diversity within a few dozen generations. A crew starting at 150 people, one of the older estimates from mid-20th century speculation, would lose approximately 80% of its genetic diversity across 30 generations. Even a crew of 10,000 loses diversity measurably over centuries. Cameron Smith's analyses argue that 40,000 people is a much safer figure, and that even this larger population would require careful reproductive planning to maintain long-term health. Our reference ship carries 40,000. This is the good news. The bad news is that even 40,000 is a rounding error compared to the genetic diversity of the human species as it exists on Earth. Approximately 8 billion people carry, between them, a library of human genetic variation that no worldship can plausibly transport. The ship carries a snapshot. The snapshot will decay. Some traits will disappear across the generations, simply through the roll of the demographic dice. Some diseases will become more common. Some resistances will be lost. Genetic engineering could partially compensate for this, but only if the ship's medical genetics teams retain both the knowledge and the equipment to perform such interventions, generation after generation, without interruption, and that is where the human element becomes the most fragile part of the entire mission, because genetic drift is only one of the ways that a starship population can quietly lose what it needs. The other, larger way is the loss of knowledge itself. Every civilization on Earth has depended on the continuous transmission of technical knowledge from generation to generation. That transmission has never been perfect. Entire fields of expertise have been lost throughout history. The specific method for making Roman concrete, the exact chemistry of Damascus steel, the navigation techniques of Polynesian wayfinders, the medical knowledge of countless indigenous cultures wiped out by colonization. And these losses happened on a planet with billions of people and thousands of independent cultures, each preserving parts of the shared human inheritance. The ship has no such redundancy. Whatever knowledge is not actively practiced aboard the ship, generation after generation, is at risk of being lost forever. Consider what the ship needs to know. It needs to know how to operate a fusion reactor, how to grow crops in hydroponic bays, how to raise livestock, how to birth babies, how to treat cancer, appendicitis, heart disease, and mental illness, how to repair the propulsion system, how to manufacture replacement electronics from stored raw materials, how to maintain the water recycling loop, how to preserve seed banks, how to interpret the ship's navigation instruments, how to operate the radiation shielding, how to repair the rotation bearings that keep the drum spinning, how to smelt metal, how to make plastic, how to make paper, how to make pencils, how to write, how to read, how to teach, how to build tools that build tools. Every one of these skills must be preserved continuously for 250 million years, or the ship loses the ability to maintain itself. Written archives help, but they are not sufficient. A book explaining how to calibrate a plasma injector is only useful to someone who already understands the underlying physics well enough to interpret it. A video recording of a surgical procedure is only useful if the ship still has surgeons trained to interpret what they are seeing. Knowledge that is not practiced decays into text, and text that is not understood decays into decoration. Any civilization that has ever tried to revive a lost skill from written records alone has discovered how much unwritten context surrounded the original practice. The tacit knowledge, the muscle memory, the intuition, the shortcuts, the warnings about what not to do is often the majority of the expertise, and it lives only in living practitioners. So the ship must maintain, across 250 million years, a continuous chain of masters and apprentices in every skill it depends on. Every generation must produce enough new experts in every field that no critical discipline is lost when the previous generation's experts die. And every generation must be sufficiently interested in continuing this transmission to actually do it. A single generation of collective disinterest, a single century in which nobody bothers to learn how the propulsion system works, because the propulsion system has been working reliably for 1,000 years without needing attention, is enough to cause an irrecoverable loss. And this is a soft failure. It looks like nothing. It feels like nothing. The ship continues to function. The propulsion system continues to run. The crew continues to eat and sleep and reproduce. But somewhere in the ship's technical culture, an entire domain of expertise has quietly evaporated, and no one currently alive is aware that they have lost anything, because you cannot know what you no longer know. The mechanics of how apprenticeship chains actually break are worth examining, because the failure mode is subtle. Consider a specific skill, say, the calibration of the ship's fusion plasma diagnostic system. This is a task that might be performed once every few years, and it requires expertise built up over decades of practice. At any given time aboard the ship, there might be perhaps 10 people who fully understand this system. 2 or 3 are senior masters in their 60s or 70s. 4 or 5 are mid-career practitioners in their 40s and 50s. 2 or 3 are apprentices in their 20s. The apprentices are learning by watching, by asking questions, and by performing supervised calibrations. In a healthy training culture, when the senior masters retire, the mid-career practitioners take their place, and new apprentices are recruited to replace the aging cohort. Now, imagine a century in which, for whatever reason, apprentice recruitment falters. Perhaps the senior masters were unusually competent, and the system did not need frequent calibration during their tenure, so nobody prioritized training successors. Perhaps a demographic bulge produced too few young people in the relevant age cohort. Perhaps a cultural fashion turned young workers away from technical trades. The reasons do not matter. What matters is that when the senior masters die, the mid-career practitioners inherit their roles without ever having received the deepest layer of instruction. And when the mid-career practitioners age into seniority, they train apprentices using an incomplete understanding of the system. 2 generations later, the ship still has 10 people who claim to understand the plasma diagnostic system, but their understanding is missing the shortcuts, the diagnostics, the warnings about failure modes, the intuitions that the original masters possessed. The system still works, until it doesn't, and when it doesn't, no one alive knows how to fix it properly. Now scale this problem across every technical field the ship depends on, and multiply by 250 million years, and the vulnerability becomes obvious. The ship is not just carrying humans and machines, it is carrying a civilization, and civilizations, historically, have never remained continuously stable for more than a few thousand years at a time. The oldest continuously functioning institutions on Earth are certain religious orders and a handful of universities, some of which have persisted for approximately 1,000 years. Nothing human has ever operated continuously for even 100,000 years. The reference Starship is being asked to maintain unbroken civilizational continuity for a duration 2,500 times longer than any human institution has ever managed, and to do it inside a single sealed vessel with no possibility of external help. Pathogens are another problem no one likes to talk about. On Earth, human beings coexist with an enormous population of microorganisms, most of them harmless, some beneficial, and some pathogenic. This ecosystem is regulated by planetary diversity. Different regions harbour different microbial populations, and travel between regions has historically allowed populations to reset and rebalance. On a closed ship, no such reset is possible. Whatever microbes departed with the crew must remain aboard for the entire journey, and they will evolve. A pathogen isolated on a small population for thousands of generations undergoes evolutionary pressure to become more transmissible, or more virulent, or less detectable to the immune system, depending on which strategies happen to succeed. The crew's immune systems will co-evolve, but they are working with a much smaller genetic library than the pathogens. Over the course of the journey, the ship will experience epidemics. Some of them will be manageable, some of them may not be. A single novel pathogen that emerges in a population of 40,000 people, with no possibility of quarantine to an unaffected region, could kill a substantial fraction of the crew before the medical teams learn to treat it. Multiple such events, across 250 million years, are statistically inevitable. Add the psychological dimension of living inside that sealed vessel for an entire lifetime, knowing that no one aboard will ever see the destination, and no one aboard was even alive when the ship departed. Every human being on the reference Starship, after the first generation, was born on the ship. They will die on the ship. Their children will be born on the ship and die on the ship. The concept of Earth is a story their ancestors told them. The concept of Andromeda is a story their descendants may or may not live to see. They are trapped in an eternal middle passage, with no beginning they can remember and no end they can hope to witness. Studies of long-duration isolation on Earth, Antarctic winter overcruise, submarine deployments, the Mars 500 simulation have consistently shown that even months to years of isolation produce significant psychological stress, interpersonal conflict, depression, and sometimes serious mental illness. Extrapolating this to a lifetime aboard a sealed vessel, and then to hundreds of thousands of such lifetimes, is genuinely uncharted territory. The ship must produce, generation after generation, a culture that finds meaning in the voyage itself, that does not descend into despair, that does not fragment into warring factions, that does not lose the will to maintain the systems keeping everyone alive. This is not primarily a technical problem, it is a cultural problem, and cultures, like ecosystems, drift. Now consider the industrial pyramid. The ship must reproduce internally. Every replacement part the ship needs, every valve, every wire, every semiconductor, every rubber gasket, every polymer film, every specialty alloy, every bearing, every solder joint must be either carried in inventory at launch or manufactured on board. Carrying enough spares for 250 million years is not physically possible, so the ship must manufacture, and manufacturing requires an entire supply chain of its own. To make a modern semiconductor, you need ultra-pure silicon, which requires specialized chemistry to produce. You need clean room facilities. You need photolithography equipment. You need dopants in trace quantities. You need extremely pure water. You need the tools that make all of these things. On Earth, the entire semiconductor industry is a global enterprise involving thousands of specialized suppliers and hundreds of thousands of highly trained engineers. Compressing this pyramid into a starship and keeping it functional across millions of years is arguably harder than any other technical challenge the mission faces. Some concessions can be made. The ship might deliberately use simpler electronics than modern Earth uses, sacrificing performance for manufacturability. Vacuum tubes are easier to build from scratch than integrated circuits. Mechanical control systems are easier to repair than digital ones, but every downgrade costs the ship capability. And even simple electronics require raw materials that must be mined, refined, and processed by machines that themselves must be maintained. The deeper question is whether the ship can reproduce its own industrial base. Can the machines that make replacement machines themselves be replaced when they fail? Can the tools that repair the tools be repaired? At some level in the pyramid, if the mission is long enough, the answer is no. There will be a critical machine somewhere on the ship that cannot be duplicated using only onboard resources, and when that machine fails, everything downstream of it fails as well. The mission ends not in an explosion or a collision, but in a slowly cascading loss of manufacturing capability that renders the ship unable to maintain itself. Vess, in the hydroponic bay, does not know any of this. She only knows that the tomatoes are not ripening. She reports her observation to the Agricultural Council. The Council notes the report, cross-references it with older records, and decides to try substituting a different cultivar from the cryogenic seed archive. The archived seeds are revived. They are planted in a separate bay under carefully controlled conditions. Most of them germinate, some do not. Of those that germinate, some produce fruit that ripens normally, and some produce fruit that behaves oddly in ways that no one entirely understands. Because the shipboard environment has changed subtly over 28,000 years, and the archived seeds were selected for conditions that no longer quite exist. The livestock problem is worth pausing on, because it captures the general shape of every closed population challenge in miniature. The ship carries some combination of animals, probably chickens for eggs, perhaps fish in aquaculture tanks, possibly small ruminants engineered for low methane output. Each of these populations, like the humans, is finite, closed, and evolving. Chickens on the ship, 28,000 years after departure, are not the chickens that were loaded. They are smaller or larger, or lay differently coloured eggs, or have subtly different feather patterns. Their immune systems have co-evolved with the shipboard microbial environment. If the ship's veterinarians revived a frozen embryo from the original chicken stock, the resulting bird would be genetically similar to the current flock, but ecologically foreign, vulnerable to shipboard pathogens. The modern chickens have adapted to, or immune to ones that no longer exist. The fish are stranger still. Aquaculture populations tend to drift rapidly under selection, and the ship's tanks are not the ocean. The fish have become something the crew's ancestors would not quite recognize. They still taste like fish. They still provide protein, but they are, quietly, a different species than the one that departed. Pathogen evolution intersects with all of this, in ways that make the medical situation genuinely dangerous. A closed population of 40,000 humans, 40,000 chickens, some number of fish, and countless microbes is a rich evolutionary laboratory. Novel diseases will emerge not from external contamination, because there is no external world, but from within the ship's own biological reservoirs. A harmless bacterium in a soil culture may, across 10,000 generations, evolve into a virulent pathogen. A benign gut microbe may cross species barriers and cause a disease no one has ever seen before. The ship's medical teams must be prepared, generation after generation, to identify and treat diseases that literally did not exist when their grandparents were alive. Some of these diseases will be manageable, some will not. Across 250 million years, epidemics are not a risk. They are a certainty. The Council files the results. The failed cultivar is retired. A slightly different one takes its place. Life goes on. But the archives are finite. Every time a cultivar is retired, the pool of stored alternatives shrinks by one. Every time a microbial culture is drawn from cryogenic storage to replace a drifted, active population, the reserve reduces. Every time a piece of stored raw material is used to manufacture a replacement part, the stockroom loses a small quantity of something that cannot be replaced. The ship is not just a vessel travelling through space. It is a slow-motion depletion event, and every day of the journey moves it closer to a threshold where the accumulated losses matter. At 28,000 years, the ship is still doing well. The population is stable at approximately 40,000 people. The agricultural systems are producing enough food, though certain traditional crops have been replaced by hardier substitutes. The medical systems are keeping the crew reasonably healthy, though certain genetic disorders that were rare on Earth have become more common aboard the ship. The technical systems are running, though certain specialized repair techniques have been quietly lost across the centuries, and no one currently alive knows how to perform them. The knowledge base is intact enough that the ship can still function. The industrial base is intact enough that most replacements can still be made. The culture is intact enough that the mission continues. But 249.5 million years remain, and every clock is still ticking. The genetic clock, the knowledge clock, the industrial clock, the ecological clock, the psychological clock. They are not synchronized. They do not tick at the same rate. Some will strike much sooner than others, and whichever one strikes first will be the one that decides the fate of the ship, not because the others were less serious, but because the first failure will cascade into the others before they have a chance to strike on their own. That is the true structure of long-duration failure. It is not one clock, it is many clocks, all running at once, and the mission ends the moment the fastest one runs out. Which brings us, at last, to the question of which clock strikes first. There is a question that has been circling this entire journey from the beginning, and it is time to answer it. Which clock strikes first? Of all the failure modes we have examined, hull erosion, radiation damage, fuel exhaustion, ecosystem drift, genetic decay, knowledge loss, industrial collapse, psychological breakdown, which one is most likely to be the one that actually ends the mission? The honest answer is that it depends on the architecture. Different worldship designs prioritize different systems, and different priorities produce different failure modes. But by comparing the timescales at which each clock plausibly runs out, we can build a rough hierarchy of what would kill our reference starship and in what order. Let us start with the fastest clocks. Psychological collapse is, statistically, the earliest catastrophic risk. The Antarctic winter overcruise, the submarine deployments, and the Mars 500 simulation on Earth have consistently shown that even carefully selected human populations under confinement begin to show measurable psychological stress within months. Extrapolating to a shipboard population living permanently in a sealed drum, the first mission-ending crisis could plausibly occur within decades. A mutiny, a factional split, a collapse of central authority, an epidemic of despair. But this clock is also the one most amenable to design solutions. A world ship with generous personal space, effective cultural continuity programs, meaningful work for every crew member, and stable social institutions can plausibly hold this clock off indefinitely. Cultures on Earth have persisted for thousands of years under difficult conditions. The ship, if designed with enough care, could do the same. The next clock is genetic drift. With 40,000 people and careful reproductive planning, the ship can plausibly maintain genetic health for tens of thousands of years, perhaps hundreds of thousands. Below that scale, the population begins to accumulate recessive disorders, lose immune diversity, and become fragile in the face of novel pathogens. Genetic engineering could partially compensate, but only if the medical infrastructure remains functional. On the timescale of the full crossing to Andromeda, the ship would need to actively curate its own gene pool, introducing artificial variation, selecting against harmful mutations, possibly reviving frozen embryos from launch-era stores for the entire duration of the journey. This is possible in principle. It requires that the industrial and knowledge base for advanced genetic medicine be preserved across every generation, without interruption, for 250 million years. The ecological clock runs on a similar timescale. Closed ecosystems can plausibly operate for centuries with careful management, perhaps for millennia with continuous refinement. But across geological time, the accumulation of unrecovered elements, evolutionary drift of species, and slow collapse of subtle biological interactions becomes an inevitability. The ship's biosphere will not fail dramatically. It will fail by attrition, one lost species at a time, one imbalanced nutrient cycle at a time, until at some point the crew is eating a monotonous diet of a few remaining hardy crops, breathing air that requires ever more intervention to keep balanced, and drinking water that carries trace contaminants the recovery systems can no longer fully remove. The knowledge clock is more difficult to estimate because it depends so heavily on cultural choices. A civilization that prioritizes technical continuity, that treats the preservation and transmission of expertise as sacred, that funds education generously, that maintains ceremonial roles for master craftspeople, could plausibly hold this clock for a very long time. A civilization that drifts into complacency during a stable century could lose critical expertise permanently. Historical parallels on Earth suggest that even the most careful cultures lose skills over long spans. The knowledge clock is not one clock, but hundreds one, for every specialty the ship depends on. And if any single one strikes at a critical moment, the consequences cascade. The industrial clock is the deepest of them all. Here, the arithmetic becomes unforgiving. Every piece of equipment on the ship has a finite operational lifetime. Every replacement part manufactured on board depletes some quantity of stored raw material. Every manufacturing tool used to make replacements is itself wearing out. The pyramid of manufacturing that on Earth involves millions of specialists, and thousands of independent factories must be compressed into a starship and made to reproduce itself indefinitely. This is where the science stops being merely difficult and starts approaching the boundary of what is physically possible with any conceivable technology. Let us be honest about where that boundary sits. If the reference starship carries a substantial inventory of spare parts and raw materials, it can plausibly last a few centuries on stored reserves alone, no manufacturing required. If it carries a well-designed manufacturing capability that can produce replacements from stored raw stock, it can plausibly last tens of thousands to hundreds of thousands of years, until either the raw stock runs out or the manufacturing equipment itself fails beyond repair. To go further to survive for millions of years, the ship would need to master something humanity has never demonstrated and does not currently know how to build. A truly self-reproducing industrial base, capable of manufacturing every one of its own components from raw material extracted from the ship's own recycled inventory, without external input, for geological time. That capability, sometimes called autotrophic industry or self-replicating manufacturing, has been theorized by engineers and computer scientists since the mid-20th century, most famously by John von Neumann in his work on self-replicating machines. But it has never been built. Every industrial process on Earth today ultimately depends on inputs, mined, processed, or synthesized by other industrial processes, all embedded in a planet-wide economy. Cutting the loop and closing it inside a starship so that the ship's industry can perpetuate itself indefinitely is a challenge that current engineering does not know how to solve. It may become solvable in centuries or millennia. It may not. So the verdict, honestly delivered, depends on which of these clocks we assume the ship can master. If we assume only the technology we have actually demonstrated, as of the current decade, the 98% water recovery of the International Space Station's life support system, the imperfect closed ecosystems of Biosphere Two and Melissa, the decades-long operational lifetimes of Voyager-class spacecraft, the reference Starship, even with generous reserves, could last perhaps a few decades to a few centuries before critical systems began to fail beyond repair. That is not enough for even the shortest interstellar journey to a nearby star, let alone an intergalactic crossing. If we assume a modestly better version of current technology, recycling loops closed to 99.9% efficiency, ecosystems stabilized through active management, radiation shielding sufficient to protect a crew for a lifetime, propulsion sufficient to reach 1% of light speed, the ship might last thousands of years, perhaps tens of thousands. This is enough to cross to the nearest star and settle there. It is not enough to reach Andromeda. If we assume a much more advanced technological level, nearly perfect recycling, genuinely regenerative closed ecosystems, radiation-hardened electronics that self-repair, robotic maintenance systems that can rebuild themselves, cultural institutions that preserve technical knowledge across dozens of generations, the ship might last hundreds of thousands of years, possibly millions. This begins to approach the scale of crossing to another galaxy, but it does not yet reach it. To survive the full 250 million years to Andromeda, the ship would have to become something we do not currently know how to build. It would have to be a fully self-reproducing artificial world, capable of not just maintaining itself, but of manufacturing every component of itself from stored raw material, and of replacing that raw material through the recovery of every atom that flows through any subsystem. It would have to sustain a genetically diverse human population that could evolve, adapt, and remain culturally continuous across 10 million generations. It would have to preserve, transmit, and continuously reinvent every piece of technical knowledge required to keep any part of itself functional. In short, it would have to fold every essential process of a planetary civilization into a single sealed vessel, and then keep that vessel running for longer than complex animal life has existed on Earth. Is this possible? The honest answer is, nobody knows. It is not obviously forbidden by physics. There is no fundamental law that says a machine cannot reproduce itself indefinitely, and there is no fundamental law that says a closed biological system cannot recycle itself perfectly. But nothing humans have ever built has come close to these standards. The distance between what we can currently do and what a full intergalactic crossing would require is not measured in engineering refinements. It is measured in orders of magnitude across multiple independent categories, all of which have to be solved simultaneously. Different architectures produce different verdicts. Consider a few alternatives to our reference ship. A smaller vessel, say, a crew of 100 people rather than 40,000 would be dramatically lighter and easier to propel. Its life support requirements would be more modest, its power demand smaller, its manufacturing needs simpler, but its genetic diversity would be catastrophically low. Even with strict reproductive management, a crew of 100 would lose most of its heritable diversity across a few dozen generations. And by the time the ship reached Andromeda, if it reached Andromeda, the descendants would be inbred to a degree that no human population has ever survived. Unless the ship carried a large frozen embryo bank and continuously introduced new genetic material from those stores, the crew would collapse long before the destination. A small ship trades genetic robustness for engineering feasibility, and that trade probably ends the mission long before manufacturing failures do. A vessel powered by antimatter rather than fusion would have vastly higher energy density and could plausibly maintain full power output for much longer. But antimatter has to be manufactured, and humanity's total production of antimatter across decades of particle physics research amounts to less than a gram. Building an antimatter economy sufficient to fuel an intergalactic starship is a project that dwarfs the ship itself in complexity. And once loaded, the antimatter must remain perfectly contained in magnetic bottles that cannot fail even once across 250 million years. A single containment failure would destroy the ship instantly. Antimatter solves the power problem at the cost of introducing a catastrophic single point of failure that persists for the entire mission. A vessel that travels much slower at, say, 1,000th of light speed rather than 100th would experience far less erosion from dust impacts and far less radiation exposure per year of operation, but it would extend the journey to 2.5 billion years. That is not a mission. That is a geological era. No conceivable architecture survives that long. Slower is safer per year, but fatal in total. A vessel that travels much faster at 10% of light speed, say, would shorten the journey to 25 million years, dramatically reducing every failure clock. But it would require 100 times more energy than our reference ship, produce vastly more dangerous dust impacts, and demand propulsion technology that current physics does not know how to build at worldship scale. Faster is safer over time but harder to achieve in principle. A vessel that carries fewer humans and more machines, a mostly automated ship with a skeleton crew of dozens, backed by artificial intelligence and robotic maintenance, solves some problems and creates others. The genetic and cultural problems shrink. The knowledge preservation problem shifts from human minds to machine archives, which are more reliable in some ways and more fragile in others. Machines do not lose skills to forgetfulness, but they do fail from radiation damage, mechanical wear, and software drift. And an automated ship still needs someone to be there when the automation breaks, which means the crew still has to preserve enough expertise to fix the fixers. A vessel with no biological crew at all, sending only frozen embryos, machines, and enough automation to raise the first generation of humans upon arrival at Andromeda, is perhaps the architecture that gives the mission its best mathematical chance. It shrinks the ecological problem to nearly zero for most of the journey. It shrinks the psychological problem to nearly zero. It shrinks the genetic problem to whatever the embryo bank can preserve. But it multiplies the machine problem by an enormous factor, because the ship must land, revive its embryos, raise them, teach them, and give them a functioning civilization on the other side, all without any adult supervision for the entire journey. This is the seed ship concept, and it is the design that most closely respects the actual physical limits of what a machine can be asked to do over geological time. It is also a design in which no adult human being ever experiences the journey. The passengers, in a meaningful sense, do not exist during transit. They only exist at either end. The seed ship architecture deserves a closer look, because it is the design that most honestly confronts the physical limits of long-duration flight. In a seedship mission, the vessel carries no adult humans at all. Instead, it carries thousands or tens of thousands of frozen embryos stored at temperatures near absolute zero in shielded cryogenic vaults. It also carries the machinery, artificial intelligence, and stored knowledge required to revive those embryos upon arrival, gestate them in artificial wombs, raise them from infancy to adulthood, and give them a functioning civilization to inherit. The engineering elegance of this approach is that it removes the biosphere problem, the psychology problem, and most of the population genetics problem from the transit phase entirely. Frozen embryos do not eat, breathe, drift culturally, or reproduce. They do not require air, water, food, or gravity. They can be stored, essentially indefinitely, provided the cryogenic system remains functional. And the seed vault can hold enormous genetic diversity, potentially the equivalent of an entire small city's worth of unrelated individuals in a package small enough to fit inside a modest section of the ship. The trade-off is that the burden of civilizational continuity now falls entirely on the machines. The ship's automated systems must remain functional for the entire journey without any human oversight whatsoever. The artificial intelligence must be robust enough to recognize arrival, initiate revival, and successfully raise a generation of children who have no biological parents. The stored knowledge archives must remain readable across geological time. Any single failure in this chain results not in the death of a crew, but in a ship arriving at Andromeda, carrying only frozen embryos and dead machines, unable to complete its final task. A related architecture is the mid-course redirect. Suppose the reference ship, carrying its living crew of 40,000, recognizes early in the journey that arrival at Andromeda is unlikely. The crew might vote, or their descendants might vote to change course, aiming instead at a nearer target such as one of the Magellanic Clouds, roughly 160,000 light-years away. This shortens the mission dramatically, from 250 million years to perhaps 16 million years. It sacrifices the original destination, but salvages the crew. Whether such a decision could actually be made by descendants who never chose the original mission is a question of politics and philosophy rather than physics. None of these architectures escapes the fundamental problem. All of them are ways of pushing failure clocks further into the future, at the cost of intensifying other clocks or accepting different trade-offs. There is no design that makes all clocks stop. So what is the verdict? For our reference Starship, 40,000 humans, fusion-powered, moving at 1% of light speed, aiming at Andromeda across a journey of 250 million years. The honest answer is that it probably does not arrive. It probably does not fail catastrophically either. It probably drifts. It probably continues to function for many thousands of years, perhaps tens of thousands, perhaps in the most optimistic scenario, hundreds of thousands. Its crew probably adapts, drifts, evolves, and continues to exist for a long time. But somewhere along the way, well before Andromeda, some critical clock strikes. The industrial base fails to reproduce a key manufacturing tool. A pandemic sweeps through a population no longer genetically diverse enough to resist it. A knowledge gap opens in a critical technical field, and the ship loses the ability to repair its reactors. An ecological cascade collapses the food supply. A cultural fracture divides the crew into factions that stop maintaining the systems keeping everyone alive. One of these clocks, or some combination of them, strikes long before the destination is reached. And when it strikes, the ship does not explode. The vacuum outside does not rush in. The hull remains intact. The propulsion may continue to burn for centuries after the last living human has died. The rotation may continue to produce artificial gravity for millennia. The empty rings will keep spinning. The dark reactor will keep humming if no one shut it down. Machines may continue to perform their small tasks in empty corridors, executing programs whose original purpose no one remembers. From the outside, the ship still looks like a ship. From the inside, it has become something else. A mausoleum, perhaps, or a sealed archaeological site, or something the language of civilization does not yet have a word for, or possibly the ending is gentler. Possibly at some point during the journey, the crew recognizes what is coming and makes a collective decision to change course. Possibly, they redirect the ship toward a nearer galaxy, perhaps one of the dwarf galaxies that orbit the Milky Way at distances the ship could actually reach. Possibly they accept that they will not become Andromedans and instead become inhabitants of the Magellanic Clouds or of some other outer halo destination, arriving a few million years into the journey with enough remaining capability to establish a real settlement. Possibly they turn the ship into a permanent installation, choosing to live indefinitely in intergalactic space, no longer aiming at anywhere, converting the vessel from a means of transportation into a home. Any of these outcomes is more likely than actually reaching Andromeda, and this, finally, is what the space between galaxies teaches us. It is not that intergalactic travel is impossible. It is not that no ship could ever cross the void. It is that the crossing is not primarily a problem of distance or propulsion. It is a problem of civilizational continuity across a duration that no civilization has ever come close to matching. The void does not attack the ship. It offers nothing to replace what the ship loses. That is a much subtler and much more devastating threat than any hostile force could ever be. A hostile force can be fought. A hostile force can be understood. A hostile force is, at least, something to push back against. The void is not something. The void is the absence of something. It cannot be fought. It cannot be reasoned with. It can only be endured, and endurance costs. Every year of endurance, the ship pays a small toll in atoms lost, parts worn, knowledge forgotten, biology drifted, crew aged and died. The void collects these tolls patiently, indifferently, forever. It does not care whether the ship arrives. It does not care whether the crew survives. It does not care whether anyone remembers. There is a strange kind of dignity in this, if you look at it a certain way. The reference Starship, for as long as it functions, is a tiny bubble of order in a region of the universe where order has almost no reason to exist. Inside its hull, 40,000 people are eating, sleeping, working, loving, arguing, teaching and dying in an arrangement of matter that has been carefully sculpted against the tendency of matter to fall into disarray. Every meal aboard the ship is a small miracle of maintained biology. Every conversation is a small miracle of maintained culture. Every child born aboard the ship is a small miracle of maintained continuity across a distance from home that no other biological species has ever attempted to cross. That the ship exists at all, even for a short time in cosmic terms, is remarkable. That it exists at all, even in the middle of a void that offers nothing, is a statement about what human civilization could theoretically achieve if it committed itself to the attempt. But the honest science says the achievement is probably temporary. And the honest science says that the question of whether a starship could survive between galaxies has to be answered by asking a deeper question first. What does survive mean? If survival means the hull remains structurally intact, the ship could plausibly survive for millions of years. Metal in a low-density environment, at low temperature, subject only to slow erosion, ages very gradually. The physical structure of the ship might persist essentially forever, in the sense that a rock persists. If survival means the mechanical systems continue to function, the ship could plausibly survive for many thousands of years, perhaps tens of thousands, with careful maintenance and generous reserves. The propulsion might burn for that long. The rotation might spin for that long. The reactor might hum for that long. If survival means the biological ecosystem continues to sustain a viable human population, the ship could plausibly survive for thousands of years, possibly tens of thousands, with active ecological management and continuous replenishment from stored biological reserves. If survival means the human population itself remains genetically diverse and culturally continuous with the civilization that launched it, the ship could plausibly survive for hundreds to thousands of years, perhaps longer with genetic engineering, before drift and isolation transform the crew into something meaningfully different from their ancestors. If survival means that the descendants of the launching civilization actually arrive at Andromeda in a form recognizable as human, culturally continuous with the people who departed, technologically capable of establishing a new civilization on the other side, then the honest answer is that this level of survival is beyond what any credible engineering study has ever demonstrated to be achievable. It might be possible with technology that does not yet exist. It might not be possible at all. The ship, in the end, is not a vehicle. It is a civilization trying to compress itself into a machine, and reproduce itself across a duration for which no civilization has ever been designed. The hull is easy. The physics of the propulsion is easy. The mathematics of the trajectory is easy. What is not easy, what is, in the final analysis, the hardest engineering problem anyone has ever proposed, is the perpetual reproduction of every essential process of a planetary civilization, in miniature, without external inputs, for longer than any life form has ever remained recognizable as itself. Somewhere out there, in a possible future that may or may not ever happen, a machine like the reference Starship might be built. It might depart. It might travel for a long time. Its inhabitants might live rich, complete lives inside a world they call home, without ever knowing any other. They might tell stories to their children about a distant place their ancestors came from, and a distant place their descendants are aiming at. And the stories might, over generations, blur into myth. The machine might carry them for 1,000 years, or 10,000, or 10 million. Somewhere along the way, one of the clocks would strike, the ship would begin to fail, and in the vast dark region between galaxies, with nothing capable of replacing what was lost, the fall would be quiet, gradual, and final. The vacuum outside would not celebrate. The vacuum outside would not notice. The Milky Way behind and Andromeda ahead would continue their slow gravitational dance toward each other, indifferent to the tiny sealed world that had briefly tried to cross the space between them. The universe would continue as if nothing had happened, because from the universe's perspective, nothing had. But inside the ship, for as long as it lasted, a species had reached farther than any species is meant to reach. And in the darkness between galaxies, that reaching the attempt itself, however doomed, is the closest thing to meaning that the void has ever contained. That is the honest answer to the question. Not that a starship could not survive between galaxies, but that survival, at that scale, becomes a question of what we are willing to call ourselves when the ship arrives. And the harder the crossing, the less certain we can be that the thing that arrives will still be us.